when gradient descent algorithm will stop, it makes the step size and goes down, and reduces the value of the parameter, the error, and going towards the minima. But when will it stop? It will always try to go towards the minima. We need some parameter to make sure it stops. It's like a kind of a base case of a recursion. Okay, so when GD will stop when it reaches maximum number of steps. Okay, so so these are also parameters which needs to be tuned, or called hyperparameter tuning. When we'll see the programming, we'll see this. So it has to have some pre-specified maximum number of steps. Okay, you have to check 1000 steps or 10,000 steps, something like that. It's usually it's 1000 plus, but there is no hard and fast anything. And also another condition is the step size is too small. Okay, so between this x3 minus x2, the gap is so small that it's 0.001 or less. In that case also we can decide, okay, stop. Okay, so we do not even need to go to the maximum number of steps, because the step size is very, very small already, and no much difference between one step to another. So one thing I would like to tell, that when we do that, first order derivative equate to 0 for easy, simple univariate equations, just straight ahead, first order derivative equal to 0, we get the value of x. But this one, the numerically using gradient descent going towards the minima, does not really go to exactly that spot when the derivative is 0, but it goes closest to that spot, kind of instead of x equal to 2, we'll probably find x equal to 1.99999, something like that. So we knew this needs to be clarified. This is the difference between just straight ahead derivating the function and equating it to 0, and the difference between the numerical method like gradient descent, where we are trying to take steps and numerically trying to go towards the minima. So here there are some limitations of the gradient descent also. Okay, we have already seen one limitation, which is that function of x has to be a differentiable at every point in its domain, and also it has to be a convex function, otherwise gradient descent will not work. It will not work when there is a discontinuity in the function. Okay, so this kind of concerns are there. But there is also another concern, is that the gradient descent only finds the local minima. Okay, it has no knowledge about a global minima. It cannot make a difference between the local minima and global minima. So once it is stuck at a local minima, and if step sizes are small, it may not ever come out of that. Okay, so it's something like, let's say we start from here in this is a function which is it's have a local minima, which is this, and also have a global minima, which is this. Now if we start from here and we have a small step size, we might kind of get stuck here. And if we have big step size, there is a chance that we might kind of shoot up and then go into this chasm and then try to find the minima. So this the gradient descent algorithm has no way to find out which one is the local minima and which is the global minima, and it might get stuck at the local minima and never find the global minima.